create a wave like this, where there's one disturbance that travels, or maybe two, then I'll call that a pulse wave, because there's a pulse of disturbance traveling along the spring. That's called a pulse wave. Here's another kind of wave. Here's a pulse. Here's two pulses, but they're still pulses. Here's three pulses, still pulses. But now when I move the wave back and forth in the same rate, in other words, I'm vibrating the spring at the same rate, this is called a periodic wave, because I am sending a wave out through the spring at a regular period, or a periodic rate. Let me stop and say that again. A pulse wave is when I send out a wave at some irregular interval. It doesn't matter how many. It could be one, it could be two, or it could be three. But if they're at irregular intervals, I call them pulses or pulse waves. If I do it at a regular interval, then I call that a periodic wave. I'm going to now increase the frequency by shaking it back and forth faster. And you can see that the waves now are coming out faster and even faster. So the number of waves that come out are not important. For a wave to be considered a periodic wave, I have to send waves out at regular intervals. For a wave to be considered a pulse wave, I have to send it out at not regular intervals. Well, as we just saw, if I took a chunk of the spring and looked at just that chunk of spring, and if you remember, that was where I put the tape on the spring, then that chunk of spring would actually vibrate up and down on my picture. Remember, on the floor it vibrated back and forth. And also, I want you to remember that the wave propagated in that direction. Another way to say that is that the wave traveled in that direction. So we have the medium vibrating in this up and down direction, but the wave traveling in that direction. I want to ask you several key questions about this idea. Number one, when you saw the tape on the wave, or on the spring, did the tape ever move from one end of the spring to the other?
No.
You never saw that tape move across the spring.
No.
It stayed where it was. Did it move? Yes, it did move, but it moved up and down. It sort of vibrated. So the first thing that I want you to know is that the medium did not travel. It vibrated. It did move, it moved up and down, but it did not travel from one place to another. That's a really key idea that I want you to focus on. All right, now that we have this idea down, that this medium did not travel. It vibrated, but it did not travel. But any fool that sees that spring, a 10-year-old would easily look at it and say, hey, I saw the wave travel from left to right, from A to B. Well, we just got through saying the medium did not travel. Say it a little louder.
Energy.
Did you hear what he said? You're exactly right. It's the energy that's traveling from one place to the other. So if I looked at my spring and said this is the beginning of the spring, point A, and this is the end of the spring, point B, then it's not the medium that's traveling, it's the energy. It's the energy travels from point A to B. So an important idea, in fact, one of the most important ideas I want you to get today, is that the medium does not travel, the energy travels. Another way to say that is that waves are energy traveling through a medium. In our case, the spring was the medium, and the wave was a transverse wave, and the energy traveled from point A to point B. To give you some more background in the vocab, or the vocabulary that I want you to use, when the displacement of the spring, when the spring had a pulse in it, that was displacing it from its equilibrium position. Sometimes it was up, sometimes it was down. Or on the floor, sometimes it was left, sometimes it was right. For our purposes, we'll call the high point the crest and the low point the trough. Crest, trough. As you can easily see, if it's horizontal, crest and trough are really the same. Crest and trough really describe the point where it is the maximum distance from the equilibrium. Now there's another kind of wave that we talked about last week. And the other kind of wave, if you remember, was the kind of wave that I used the slinky to demonstrate. And then another kind of wave, I would smash the slinky together, and then I would let it go, and it would fling out like this. So there would be some points where the slinky itself was smashed over to the side, and other points where it would expand in this direction. So the movement of the slinky was left and right like that. And the wave propagation, was in this direction. So this is a different kind of wave. It's a kind of wave that is sometimes called the compression wave. Because first there'd be a compressed part, and then there'd be a rarefied part. So that's more vocab. The compression part is where they're smashed together, and the rarefaction part is where they're stretched out away from each other. So what we have is compression, rarefaction. Compression, rarefaction. Everybody say rarefaction.
Rarefaction.
It's a weird word, but it just means the opposite of compression, where it's stretched out. Sometimes these kind of waves are called compression waves. And so, while I will label the longitudinal wave, and it's longitudinal because the medium is vibrating in the same direction or in the direction parallel to the wave propagation. Okay, so I have two different things that I've described to you today. Most of this is review, but some of it is new. We have a transverse wave where the medium is vibrating perpendicular to the direction of the propagation of the wave. There's crests and troughs that describe the points where the medium is displaced maximum from its equilibrium point. And then there's the longitudinal wave, which is sometimes called the compression wave. You can see why. Which has compressions and rarefactions, compressions and rarefactions. And you can tell the longitudinal because the medium, in our case the slinky spring, vibrates in a direction that's parallel to the direction of wave propagation. So those are two things that I want you to know, two kinds of waves I want you to know about, the transverse and the longitudinal. A pulse wave is taking an equilibrium spring, or a spring that's at equilibrium, and disturbing it, or causing an energy wave to move from point A to point B. We've already focused on, with our look at transverse waves, that this piece of the spring does not travel. It simply remains at equilibrium or moves up and then back down. In other words, this piece of the spring moves up and down, but it doesn't move from left to right. And so it's the energy. A pulse wave transmits energy from point A to point B. It doesn't transmit any material. It transmits energy. And so the important idea to get from that is that energy is being transmitted through a pulse wave. And why do I call it a pulse wave instead of just a wave? Because a pulse wave is maybe one or a short burst of pulses, but it doesn't come at a regular interval. If it comes at a regular interval, I'll call that a periodic wave. A periodic wave is one that comes at a regular period or interval. A tuning fork attached to a waveguide. I'm going to demonstrate for you what it does, but first I want you to take a close look at it. I'm going to strike it with this mallet, and then I'm going to ask you to take a look at and pay special attention to that tuning fork, because I'm going to ask you to tell me what you see. Okay, here we go. Okay. I heard almost everybody saying the same thing. Tell me what you saw. Did you hear what he said? He saw this fork vibrating back and forth. When I hit it, it would deflect and then bounce back and forth. That's the job of a tuning fork. It vibrates back and forth. So the key thing I want you to know about a tuning fork is that when it's struck by a mallet, it vibrates back and forth. What's happening is that this waveguide is compressing air molecules. I have here a picture of air molecules, and these air molecules coming out of the waveguide like that. When the waveguide compresses them, it smashes the air molecules together. But then when the tuning fork goes the other direction, it pulls the air molecules apart. And so it compress, rarefy, compress, rarefy, compress, rarefy. And so if you could see the air molecules, they would look something like that coming out of the waveguide. Where these parts right here represent the compressions, this part right here represents the compressions, and the parts in between represent the rarefactions. And so a sound wave is a compression wave or a longitudinal wave that compresses the air molecules and then rarefies them, and compresses and rarefies. It vibrates back and forth like this, and when it goes in this direction, it compresses the air molecules so that they become smashed together. That's called a compression wave, or a compressed portion of the wave. But then when it goes in the other direction, it stretches out or rarefies the air molecules, and then with each vibration it gets another compression portion and another rarefaction and another compression. And the really key idea that I want you to see here is that here, here, and here, the molecules of air are pushed together or smashed together. And this is called a compression wave. And rarefactions, right here. And this continues on as long as the tuning fork is vibrating. Now, I want to be careful and not mislead you. The sound waves that come out actually come out as spherical waves. That means that they start as a ball bulging out, and they turn into bigger and bigger balls, like first starting the size of a softball, then growing to the size of a basketball, then growing to the size of a beach ball. And so, if I were to draw it in 2 dimensions, it would look like this. But if I just draw it on the board, I might just focus on this portion right here, and these are the parts coming out of the tuning. Are you asking me why does sound become less and less intense, or why does it sound quieter and quieter the further away you go?
Yes.
That's a good question. Here's the reason why. Keeping in mind that sound is actually a spherical wave, the energy that's in the sound always stays the same. So let's say I have 20 joules of energy here at this wavefront. I'll also have 20 joules of energy here, and 20 joules of energy here, and 20 joules of energy out here. The energy never becomes less. So then why does it sound quieter out here?
It's not concentrated.
Because it's more spread out, exactly. Say it louder.
Because it's more spread out.
Because the energy is more spread out. Does that make sense? And so that's why you can't hear sounds that are far away. All right, that's good. What I want you to do now is look at what I've written here, look at what I've written here and here, combine that with our demonstration for today, and I would like you to know these terms. One key idea that I'd like you to have is that sound is a longitudinal wave, because they're using the crests to represent compressions, and then they're also using the troughs to represent the rarefactions. So this symbol represents compression and rarefaction, and I want you to not get confused on that, because a lot of students, sound is a longitudinal wave. Sometimes it's called a compression wave. Sometimes it's called a compression wave. All right? How about this? Sound is the transfer of energy. From point A to point B. If this is point A right here, if this is point A, then sound is transferring energy from point A to point B. Sound is the transfer of energy from point A to point B. In fact, as a generalization, all waves transfer energy from one point to another. They never transfer matter. They never transfer the medium. So when I'm talking to you right now, the air that comes out of my mouth does not travel across the room and hit your ear. It vibrates like the spring vibrated, but it doesn't travel. What travels is the energy. So I want you to be able to distinguish between what's traveling and what's vibrating.